balance, so you tend to experience things with sound and with light in a logarithmic sense, because the logarithms let you look at a huge range of things. And so apparent magnitude is how bright a star appears from Earth. And there's this crazy reverse scale, but good astronomers can tell you the apparent magnitude with 2 sig figs. And the way they do that is that there are certain stars in the sky, like that one is exactly a magnitude 4, and that one's exactly a 3, and that's a 2, and that's a 1, right? And so they can sit there and look and go, okay, and they can get it. They can get it down to like, that's a 3.7. Yeah? That's pretty impressive. Good amateur astronomers can just look and eyeball a star and get the magnitude, right? But it's a crazy backwards scale. If you look at this, what's happening to this is that the B is in the denominator, right? And so if B is a really big number, that's actually a negative, yeah? That actually becomes negative. So like a -1 is a really, really bright star. It's a strange thing, right? So the magnitude, this little m, this is the apparent magnitude, is 2.5. And this is, I believe, not in the data packet. This is log 10, touch unexpected. And then this 2.52 times 10 to the -8 seems vanishingly small for a brightness, but it's the brightness of just an ordinary bright star. And then we divide by the brightness of the star you're looking at, and we get the apparent magnitude, right? So the smaller B is, the bigger M is. Yeah? Okay. And so if we multiply the brightness by, if we multiply the brightness, right, is going to be M minus 5. Isn't that wild? This is supposed to be a B, right? B times 100. 100 times the brightness draws your apparent magnitude down 5. Yeah? So a magnitude 0 star, okay, is 100 times brighter than a magnitude 5 star. Yeah? It's subtract 5, not divide by 5, right? That's how logarithms work. So let's look at this guy. What is the apparent magnitude of a star with a brightness of 7.2 times 10 to the -10th watts per square meter? Well, I can do that, right? It's 2.5 log, and then I'm going to go 2.52 e minus 8 divided by 7.2 e minus 10, right? So type that into your calculator. I'm doing this first one here, and then I'm going to do that one. This one's 100 times less bright, so it should be an M of more, 5 more, right? So this guy is 2.5. Be sure to use log and not ln, times log 2.52 e minus 8 divided by 7.2 e minus 10. What's funny is that the IB folks don't give you this one, but they give you one based on this one, which is, I suppose, okay. So this is 3.86. Is that what we get? Yeah, so M is 3.86, right? So now let's do the star that is less bright than this, right? Everything's the same, only this is 7.2 e to the minus 12th, right? So I'm just going to hit second entry, go back and put a 2 instead of a 0, and the answer is 8.86, right? Right? Isn't this guy's dimmer, but the magnitude is 5 more, exactly 5 more. It's not that we multiplied by 5, it's that we added 5, correct? Yeah? That's the way logarithms work, so it's a factors become just adding something to it, right? Okay? And there are no units for magnitudes, they're just pure numbers because it's just an arbitrary scale. Now before we go and calculate something here, okay, no units, no units. Here's sort of the scale, and I just love this thing. This is from my 1970 something astronomy textbook, right? So it was already outdated by the time I went to college in 1981, right? Okay, but here's the sun. The sun is minus 26.8, right? Yeah, that bright object outside is the sun. Okay, minus 12.6 is the moon. The full moon is really bright. In fact, if you got a big diameter telescope, big diameter telescopes are there to look at faint objects. So if you look at the full moon with an 8-inch telescope, it kind of hurts your eyes. Yeah? You might want to like cover part of the aperture or just make your own filter, just cut some holes or something that reduces that if you're going to look at the moon. The big telescopes like that. Venus is pretty bright. In fact, Venus, there's there's an airport in the Pacific Ocean. I can't remember, some island, right? And they keep track of how many times they clear Venus to land. Unidentified 059er, you are cleared to land on West Runway 15905. Yeah? As you look up and Venus looks like an airplane with its landing lights on, approaching the airport, right? And every now and then a radio controller is like, yeah, go ahead. You've made no radio contact with us, but go ahead and land. Because you're going to anyway, right? Because, out in the middle of the Pacific, sometimes you just got to land, don't you? Right? Okay. Mars is pretty bright. Mars can get brighter than the brightest star when it's just in opposition. It's just opposite us. It's pretty close to us, right? And then Sirius is, of course, seriously bright, right? The second brightest star is Canopus, but that's a whole nother can of peas. Right? And then 6 is the faintest stars that you can look at, right? So 6 all the way to minus 1.4, those are the stars that we can, there's not that big a range, right? Okay. So to see Pluto, you've got to gather more light in a bigger area than your eyeball, right? Your eyeball has a relatively small aperture, right? You need a big old thing, right? 8-inch telescope, I think at least 16 is better for Pluto. Quasars, this is a galaxy, okay? So if you can see this, you're seeing something in a different galaxy, because quasars are, I believe, in other galaxies, most of them, right? Kitt Peak, you can see 24.5. And then this is the greatest one. Faintest objects observable with the space telescope when it is launched. In the distant future, the year, the year 1980 something. When was it launched? Hubble. So minus 27 is burn your eyes out. 1 is a normal bright star. 6 is barely visible to a naked or unclothed eye, but you can't see anything if you close your eyes. Right? So a magnitude 1 star delivers 100 times more watts per square meter than a magnitude 6 star. This is weird. I don't know why. Why did they do it that way? Don't know. I would set it up the other way, but I wasn't there. All right. What is the apparent magnitude of a star? Is this an example? That's a whiteboard. Okay.
So you have to rent it.
The distant future. The year 2000. Yeah. Yeah. Yep. What units? I know, I'm just checking you.
That one unit, Good. What unit? I'm making a new unit. There's the unit.
It's called an Ericsson. Watts. Yeah, there you go. That's good. Because, what is it? It's a what? This unit is actually, here's how you say it. You just go. Yes. Yes. It's a. Yeah. It's like you guys know John Ing? Yeah. That's right. You know how you pronounce his name? There's no I. It's just, that's right. I taught his sister, so I can make fun of his name. We really shouldn't make fun of it because some countries, I mean, very, very impoverished countries, people can't afford vowels for their names, like the Balkans. Yeah, if you go to the Balkans and stuff like that, right? They've got, or the Ivory Coast, right? Isn't the guy